Okay, so this is our last section for this unit. So this is our beginning half of series, and then we'll do another unit on series from a little bit different standpoint. So this is our last test that we're going to do for this chapter, and then we'll have another test and some other things in the next chapter, and then again kind of a different format. So here we're going to talk about alternating series. So a lot of our tests have required that the terms are positive and things like that. And so this one will definitely be not that. So this is going to be alternating. So they're going to be positive, negative, positive, negative. Okay. So the harmonic series. So we know that the harmonic series, this is why you need to know the name of it, because we know that it diverges. Okay. So we know that this harmonic series diverges. But what if we wanted to have this series alternate? So what if instead of it being all positive numbers, we wanted it to alternate? So what would we need to do to make that happen? So that's the series that we have. So what could we multiply it by? Well, we know it would have to have something to do with -1, but we can't just keep multiplying by -1 every time, because then you're just going to get you're going to just keep multiplying by -1. You're just going to get negative terms. Okay, so if I take 1 over n and take it times -1, I'm just going to keep getting negative. So sometimes I want it to be positive, sometimes I want it to be negative. So that means we want to put an exponent there. And so I call this the alternator. The -1 to the n is the alternator, because if I plug in n equals 1 into this, then I'm going to have -1 to the first, which is -1. So that means the first term here is going to be negative. If I plug in n equals 2, then my second term will have -1 to the second. Since that's an even power, that's +1, so then it would be positive, and so on. The other alternative, so that one would start negative. So if I didn't want to start negative, I could do -1 to the n minus 1 or the n plus 1. It doesn't matter. And then now I'm going to start off with a positive value. Okay. So if I were to look at the sums, the partial sums of this new series. So if I were to look at the, using this one here, I'm going to write down the partial sums. So I would have, and I'm going to write them right here. So I would have S1 first term. So adding them up, I just get a 1. So if I plug in 1, I'll have 1 over 1, and then I'll have -1 to the 0. So that's going to give me a 1. So the next partial sum means that I'm going to plug in 2, and then I'm going to add that number to the 1. So I know that when I plug in 1, I get 1. And if I plug in 2, I get 1/2. But then I have -1 to the 2 minus 1, which is negative. So I'll get -1/2. And so that sum, of course, will be 1/2. And then S3 would be 1 minus 1/2. Well, then now you can kind of see, okay, so the next term will be positive. So I get 1 minus 1/2 plus 1/3, which will end up being 5/6. And if I do S4, I'll get the previous term, which is 5/6. I'll get that previous sum. And then it was plus 1/3, so this will be minus 1/4. And so this sum is 7/12. And then we'll do one more. If I do the fifth one, it'll be the last sum, 7/12. And this last one was minus, so this will be plus 1/5, which is going to give me 47/60. Well, if I were to use this number line and kind of try to show where these sums are, so let's put them on this number line. So let's go 0 and 1, because all my numbers are between 0 and 1. My first sum is right here. S1 is 1. S2 is 1/2, so 1/2 would be right here. So this would be S2. And then S3 is 5, 6. So that's down this way. That's 5, 6, and that's my third sum. And then the next sum is 7 twelfths. Well, 7 twelfths is closer to a half. So here's 7 twelfths. That's going to be my fourth partial sum. And then I'm going to have 47 over 60, which is going to be this direction. And that's my fifth one. So if we kind of look at what's going on here, we can see that you're going from 0 to 1. And then you're going from that's your first sum. And then your first sum goes back to 1/2, goes this way. That's S2. And then S3 goes up to 5 sixths, and then S4 goes back to 7 twelfths, and then S5 goes here. So you can see that your sums are going to oscillate, but they're just going to continue to keep getting smaller and smaller and smaller. So the difference is, because of the alternator, this series will actually converge, because that sum is just going to keep doing that same thing. It's just going to keep going this way until it's smaller and smaller and smaller. So my sequence of partial sums will actually converge to something. Okay, so putting that alternator in helps me because I'm adding, then subtracting, then adding, and then subtracting, and then adding, and then subtracting. So it helps it converge better. So what's going to be really awesome is an alternating series is a series that must alternate positive and negative. Okay, so as soon as I determine I have an alternating series that I'm alternating positive and negative, an alternating series is terms who alternate positive and negative. It doesn't matter if I start positive or start negative, they just have to go back and forth, positive, negative, positive, negative. So here's what's awesome about it. It's much easier for an alternating series to converge. So the harmonic series diverges, but the alternating harmonic series, which is the one we just looked at, actually converges. Okay? So we know that if we have these conditions that are met, then we will end up having an alternating series that converges. Now, I'm not going to actually have you ever state number one. So you're first going to just say, hey, I have an alternating series. If I take the limit of the a sub n, so not including the alternator, notice that this part's a sub n, no alternator. If I take that limit and I get 0, and it's true that we get a sub n plus 1 is less than a n for all n. So that means is it's decreasing. So a n plus 1 means the next term. So as I go to the next term, it's always less than the previous term. That's what this is saying. So in words, much easier. Verbally, we're saying that we have to have something that alternates. So it's an alternating series. It decreases in magnitude, and it has a limit of 0. Okay? So one thing to be real careful about is, let's say the limit is not 0. Then you do not say that it diverges by the alternating series test. The alternating series test can only be used to prove convergence. If the limit is not 0, then it diverges by the nth term divergence test, not the alternating series test. Okay, so that's the only thing that's important here. Getting a limit that's not 0 doesn't mean the alternating series test showed it diverges. It means that it diverges by the nth term divergence test, which is this first test that we're always going to do. Okay, so let's look at an example and find out whether these series converge or diverge. Okay, so for our first series, we have to determine if those things are met. So first of all, I need to say this is an alternating series. Just like we start off saying, hey, this is geometric or this is a p-series, say this is an alternating series. And then need to say that the limit as n goes to infinity of 1 over n squared. Do not include the alternator. That limit is most definitely 0. And the second thing I need to show is that the 1 over n plus 1 squared, is that in fact less than 1 over n squared. So is the n plus 1 term, if I go up 1 term, do I end up always less than the nth term? Well, clearly you do, because you're going to add 1 to the denominator and square it. So this denominator over here is obviously much larger, no matter what. And so therefore, this is going to work. And so you've got that, which we could also say, and this is for n greater than or equal to 1. So again, it doesn't matter what happens otherwise, but this is what's going to happen. You can also say that it, you can say the words that it decreases in magnitude. So another way to do that is just say it decreases in magnitude. Sometimes I think it's really nice for you to just show this inequality, but sometimes you can't figure out if that inequality is true, but you know it's getting smaller, so just say it decreases in magnitude, and you're kind of covering that. And the limit was 0, and so you're going to say therefore, and then always rewrite your original series. Therefore, this series converges by the alternating series test. Okay, so notice that we don't have to use P series, we don't have to use geometric series, no integrals or anything. All we have to do is show that the limit is 0, state that it's alternating, and then show that it's decreasing, or it decreases in magnitude, and then you're good. So it's much, much easier for a series to converge if it's alternating. Okay, so let's look at the next one. So again, the first thing I need to say is this is an alternating series. Well, look carefully at that and figure out, why am I saying it's an alternating series? What makes it alternating? Well, what makes it alternating is this, and I call it the alternator. The -1 to the n plus 1 is what's going to make this alternate. Okay, so every other term is going to be positive. So you're going to go positive, negative, positive, negative, positive, negative. Or I guess actually this time you start negative. Because if we plug in 2, because this one starts at 2, if you plug a 2 in there, you'll get -1 to the third. So this one starts negative. So it's an alternating series. The limit as n goes to infinity of the an, not the alternator, so just the limit of this general term. This is definitely 0. We know how to do these limits. The power on bottom is bigger. And then we can say that the an plus 1 is less than the an term for n greater than or equal to 2. Now, again, I don't really have to show that because it should be pretty clear that that's happening, because if you plug numbers into the bottom, you're going to always be bigger than the top. So even though the top is growing, the bottom's growing faster. And for fractions, that means it's smaller. Okay, so we can just state that. And so therefore, your original series, n equals 2 to infinity, -1 to the n plus 1 times n squared over n cubed plus 1, converges by the alternating series test. Do not abbreviate, no matter how many places you read it, how many people tell you you can do it. Do not abbreviate. Even if the answer key abbreviates, ignore it. Do not abbreviate, okay? So say alternating series test. And always give the reason. Always, always, always. Okay, so C. So again, I have the -1 to the n plus 1, so I'm going to say this is an alternating series. So I need to say that first, because then that tells me what I need to show. So first of all, the limit as n goes to infinity of n over 2 to the n is going to equal 0. Now, you could use L'Hopital's rule, but 2 to the n is an exponential which grows way faster than n. So this is definitely getting the bottom fast growing, top very slow relative to that. So this limit is definitely 0. And then we need to say that the a n plus 1 is less than or equal to the a n term for n greater than or equal to 1. And if you wonder if it's true, you could always plug some numbers in and kind of see what's going on with that to see that it's getting smaller. But again, you can visualize that it has to be getting smaller because 2 to the n is going to grow so much faster than n. And if the bottom is bigger, then your number is smaller. Okay, so it's got to be getting smaller. Therefore, this series n equals 1 to infinity, negative 1 to the n plus 1, n over 2 to the n converges by the alternating series test. And again, don't get lazy. Practice what you want, because then when you get on the AP test, you don't have to even think about it. You just go ahead and do the problem and you're good. Okay, so now let's look at one where it's a little bit harder to prove this is decreasing, okay? Because this one, the other ones were pretty clear. The bottom was way bigger than the top. Well, now both of these grow pretty slow. So even though it's bigger, let's use the derivative to prove that this is decreasing. So if we look at f prime of n, so we do the derivative of this a sub n term, we're going to get bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. If we simplify this, we're going to have 1 minus ln of n over n squared, and we want to find the critical points. Well, one critical point would be when n equals 0, but 0 is not in the interval here. So the other one would be to solve when does 1 minus ln of n equal 0. Well, that's going to equal 0 when ln of n equals 1, which is going to be for n equaling e, because e to the first is e, okay? So that means we can do a little sign chart here, starting at 1 and going to e, and then we have after that, and we need to look and see what's happening. So f prime, if I go between 1 and e, so like if I were to plug in a number between 1 and e, well, we're going to end up with, if we plug in something like, we plug in something for n like 2, you're going to have ln of 2. Well, that's going to be a number definitely less than 1, because ln of e is 1, so numbers less than e are going to make that thing less than 1. So you have 1 minus something less than 1 over 2 squared, if that 2 is the number we try, so we're going to get positive here. And if we pick a number bigger than e, like, you know, 1,000,000, 1 minus ln of 1,000,000, well, ln grows and goes to infinity, so you're going to get 1 minus infinity over an infinity, so you're going to get negative. So that means that f here increases and then decreases. So as long as we're greater than e, we do get it decreasing, okay? So we will say 1, the limit as n goes to infinity of my a sub n, my ln of n over, oh, not n squared, just over n, that this limit is going to be 0 as I go to infinity. The reason for that is again, that relative growth. ln of n is one of the slowest growing things that we have, and n is still going to grow faster than that. So that limit is still going to go to 0. And 2, we just showed that an plus 1 is less than or equal to an for n greater than or equal to e. Now remember, for convergence, it doesn't matter if it converges, as long as it converges eventually, it converges. So it can do some, if it converges eventually, then it has to converge, because you would just be adding finite things at the beginning. So therefore, my original series, or n minus 1, ln of n over n converges by the alternating series test. And please practice writing out all the justifications so that it's so much easier to figure out. Okay, so for this, this is a really, really, really important bit of information, okay? So if you have an alternating series, then we can actually, if we use the partial sum to approximate the values, okay? So say we're adding up a bunch of terms, and we're not going to add to infinity, so we just want to get an approximate answer. Well, we might add up 7 terms, okay? So we would find S7. Well, the most that we can be off from the real answer to what the series is if I add to infinity is whatever the 8th term is. The first unused term is the most that we can be off, okay? So if we know that we have all the criteria that's met and we know that it converges, okay, then we know that the remainder, okay, the remainder is what I get when I subtract the sum that I use to estimate. So say I add up 7 terms, I subtract that from the actual sum that I probably don't know. So what I know then is that I would get the remainder. Well, I know for a fact that that remainder is less than the n plus 1 term, okay? So if I add up a bunch of terms, I know that I'm as close to the actual answer, I am less than or equal to whatever the first used term is. That's how far off I am at most, okay? So as long as you know that it converges and you want to get an estimate for what the actual sum is, because remember, it's really hard to find the actual sum of a series. We can do it for geometric, but hardly anything else. And so we can't find the sum, but we could approximate it by adding up, say, 15 terms. Well, the most I can be off from the actual answer is whatever the value is for the 16th term. Okay, that's the most I can be off. So we say that's the error band. Okay. So we're going to look at an example here. So let's say that I wanted to approximate this sum, this series. So I want to approximate, what do I get if I were to add this up all the way to infinity? So I wrote down all the numbers, and instead of just adding this many, what if I went all the way to infinity? That's what I'm trying to approximate. So what we do is we just say, okay, well, we're just going to add up this many terms. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So I added up 9 terms. The most that this answer, this sum, the most that I can be off is whatever the value is of the 10th term in absolute value. Well, the 10th term is going to be 1 over 10 squared, which is 1 over 100, which is 0.001. So that means that or 0.01, sorry, not 001, 0.01, 1/100th. So that means that I know that the actual value of adding up all the terms all the way to infinity is plus or minus 0.01 of the 0.828. Okay, that's how close I know that I am. Well, if we use the calculator, we can sum up the first 200 terms. Okay, so that in this, filling this in, the next unused term is -1/100. Therefore, the error in our estimate is at most 0.01. That's the most I can be off. So use my calculator to find the sum of the first 200 terms. Well, guess what? In your calculator, and I'm not going to open the calculator thing, I want you to do this. There's actually a summation. If you go on the calculator page, you go to Calculus. When you choose the menu, you'll see summation. You can actually put in n equals 1 to 200 of -1 to the n plus 1 times 1/n squared. You can put that in the calculator and it will actually give you that sum. So it's going to tell me if I add up the first 200 terms, I get 0.0822455. So what's my error from adding up the first 200 terms? Well, my error is going to be the 201st term. Whatever that value is, which would be 1/201 to the second, and really it's the absolute value of that term, so I don't bother to write down the -1 to the whatever because I'm absolute valuing it. So this is going to be the most that I can be off, and you can put that in the calculator and find out that you're at most off. If you add 200 terms, you're at most off 0.000025. So that's really close. You are correct in these 4 decimal places. So that's pretty good. And I only added 200 terms. Okay. So here we're going to approximate the sum of the series using the first 4 terms. So we're going to say, okay, so the sum is approximately, let's plug in 1. So if I plug in 1, this one's going to start positive. So I'm going to have 1/1 factorial, and then it's going to be minus 1/2 factorial plus 1/3 factorial minus 1/4 factorial. So if I do that in the calculator, I'm going to get 0.625. That's going to be what I get when I add up the first 4 terms. So then it says, explain why, and this is a very typical AP question, explain why the estimate that we found differs from the actual value by less than 1/100. So we would say, because the series is alternating, the error is going to be the absolute value of S minus S4, so that's the difference in those two things. We know that that has to be less than the absolute value of the 5th term. So that's going to be -1 to the 4th over 5 factorial. Well, that happens to be 1/120, which is less than 1/100, which is what we were asked to show. Okay, so that means the error is less than 1/120th, which is certainly less than 1/100. And then explain why the sum cannot be 0.7. Okay, so our estimate is 0.625. We are at most, the worst case scenario that we can have is that we are 0.625 minus 1/5 factorial, or 1/120th, and then that would be my actual sum is somewhere in the middle of my estimate that I found, which was 0.625, either minus that or plus that amount of error. That's the most that I can be off at all. I can't be worse than that. And if we do this in the calculator, we get 0.61666 is less than the actual sum, is less than 0.6333. So what that means is the actual sum is somewhere between 0.61666 and 0.6333. Therefore, the sum cannot be 7. Okay? 7 is not in the interval 0.61666 to 0.6333. So the sum cannot be 7. Okay? So I know that the real sum is somewhere between those two things. Okay? So that's how we use error. And we'll learn other kinds of error and stuff later. So the last thing that we have to talk about is absolute convergence and versus conditional convergence. So I'm going to actually cover this in class. So you can kind of read over it, but I think it's a little bit easier explained in class, and then we'll go through these last examples, and then you'll be able to finish up the section. So you're really going to keep doing the same thing. This is just terminology. So something is considered absolutely convergence if it converges with absolute value. Okay, so if I put absolute value bars around it, it still converges, then it's called absolutely convergence. If a series is absolutely convergent, then it is convergent. So in other words, if I can prove that the series converges if I stick absolute value bars in, then I've proven that this one works. Okay, so that's what absolute convergence means. It's kind of a stronger convergence. Conditional convergence means it converges if I have the alternator in, but if I take the alternator out, I do absolute value, it's not convergent anymore. Okay, so we'll see some examples in class that'll help bring that home a little bit about what that means. But I just like to think of it as it's a stronger convergence. Okay, so it means that it'll converge with or without the alternator. Because remember, what I talked about in this video is it's a lot easier for things to converge if you have an alternator. Okay, so if I don't have an alternator, it's harder. So if it does converge that way, then that means that that's a little bit stronger convergence. So that is it for this video. We'll continue the rest of that in class.